Good morning. So today, which is our last lecture of the semester, we're going to be talking about a couple of topics. One is scattering of identical particles. So far we've been talking about scattering of a single particle off of a potential, which would also hold in the case that you had two non-identical particles by just going to the center of momentum frame. But some different things happen if you have two identical particles. So first, consider two identical bosons. And to make things simple, I'm going to assume that these bosons have spin 0. They could have spin 1, which would make things a little more complicated. Okay, but we're going to take them to have spin 0. And so examples of this would be alpha particles, pions in nuclear physics, and even photons. Well, no, sorry, photons are spin 1, so they wouldn't go in this category. But so when we have two identical particles, we have to consider the total wave function. And so fortunately, in this case, there's no spin. So I can just write the total wave function as a function of the two labeled coordinates. And in general, I can find solutions to the Hamiltonian, the Schrodinger equation, that are going to break down like this. So first of all, there's a piece that goes like the sum of the two position coordinates. And then there's another piece that goes like, I'm writing a different psi here, that goes like the difference of the two coordinates. Okay, and if our Hamiltonian is invariant under translations, then this part right here is just describing the overall motion of the whole center of momentum. So that's the center of momentum motion, which is just a plane wave. And then the other part of the wave function here is the relative motion of the two particles. And one thing we know is that because these are bosons by assumption, and they're identical, and there's no spin to worry about, this must be symmetric if we interchange the two coordinates. So if I take the coordinate describing particle 1 and I interchange with the coordinate describing particle 2, it should be symmetric under that. And so that means that the relative wave function has to obey that if I replace r by minus r, I get back the same thing. Because replacing r by minus r is the same thing as interchanging the coordinates of the two particles. So that means this thing has even parity. That's the definition of even parity. And so if we think about what does this mean for scattering problems, before, when we were talking about a single particle or two non-identical particles, we had a scattering wave function. I'm going to leave off the factors of 2 pi to the 3/2 because they're not going to matter today. So we had an incoming beam part, and then we had a scattering amplitude part. Okay, oh, and I should put my 1 over r. But instead of that, because we have two identical particles, it's got to look something like the following. That my total wave function has a part describing one incoming beam plus the other incoming beam. So notice these are moving in opposite directions. And then there's a scattering amplitude that depends on theta, but it has to come with another part that depends on pi minus theta. And the reason for that is so that this thing will be the same for r goes to minus r. So there's a factor of e to the I k r over r. If I replace r by minus r, the magnitude of r doesn't change. So that's why this part stayed the same. But the angle part changes. Instead of theta, I have pi minus theta. Okay, so this is the incoming beams. This is one incoming beam. This is the other incoming beam. This is one outgoing particle. This is the other outgoing particle. And so now if we just repeated everything, I'm not going to go through the details, but if we repeated everything we did to understand what the total differential cross-section is, it's going to be the sum of these two scattering amplitudes at theta and pi minus theta. I take their sum and then I square it. Okay, and so now I can take that and just expand it. So one term is the square of the first term, and one term is the square of the second term. And then I have the cross terms of this times the complex conjugate of that, and then this times the complex conjugate of that, which assemble themselves into 2 times the real part of fk star of theta, the complex conjugate, times fk of pi minus theta. Okay, so that's the form. Of course, I'm not telling you how to solve for fk of theta. I would have to give you the potential between the two particles, and you'd have to solve the Schrodinger equation. We're really today just talking about the form of the answer. Solving for the scattering amplitude is a whole nother story. But okay, if I'm going to do this scattering and I have indistinguishable particles, then the interpretation of this is that I've got one amplitude to do that. So this is one scattering process. And I've got another amplitude to do this, where they scatter like that, where this angle is theta, and this angle is also defined to be theta. And if I'm at a detector far away, all I know is I see a particle there, and I see a particle there, and the same thing over here. So those are equally likely amplitudes for this process. And so I have to add them together in order to get the answer and then square it. So one interesting thing that comes out of this is, let's say I look at right angles to the beams at theta equals pi over 2, then we're going to get constructive interference. And all that means is that if I look at this term and this term, those are actually going to be the same if I plug in theta equals pi over 2. But not only that, but they're the same as this term when I plug in theta equals pi over 2, which will be real, so the real doesn't do anything. And then I get 2 more, and so I get a total of 4 times as much. Not twice as much as you might have thought, perhaps. So the differential cross-section for theta equals pi over 2, right angle scattering, is 4 times the scattering amplitude magnitude squared. Okay, another thing that you can tell is, let's say we take our scattering amplitude and we did a partial wave expansion on it, then only even angular momentum partial waves will contribute. So even L partial waves contribute. And so let's see quickly how that comes about. We are taking Fk of theta plus Fk of pi minus theta. Okay, and so the first one is a sum over all L's of 2L plus 1 times the Legendre polynomial of cosine theta. That's telling you that it's L angular momentum times some coefficients FL of k. But then I'm supposed to do the same thing with pi minus theta. So it's actually got the same factors. And now it's cosine pi minus theta here, FL of k. But when you plug in for the Legendre polynomials at theta goes to pi minus theta, you just get a factor of minus 1 to the L. And so that means all the odd terms are going to go away and all the even terms are going to get twice as big. So this is 2 times sum of L even of our factor of 2L plus 1, our Legendre polynomial, and FL of k. Okay, so you don't get odd angular momentum partial waves when you're scattering identical spin 0 bosons. Okay, it's actually more common to encounter identical spin 1/2 fermions, for example, electrons. So now let's consider that case. So identical spin 1/2 fermions. And now there are 2 cases to consider, because we can consider what the total spin is, sort of like we considered for neutron-proton scattering last time, except now we have identical particles, so we have to be even more careful. So one case is if the total spin is 0. Okay, that means, as we learned, for example, from studying the helium atom, the spin state is antisymmetric. And we know the total state has to be antisymmetric under interchange of the 2 fermions. So that means the spatial state has to be symmetric. So the spatial wave function, everything not describing the spins, is symmetric. And so that means in particular that psi of r is psi of minus r. Okay, and that means that everything goes through just the same way it did for bosons. That's if they're in a spin 0 state, they go just like spin 0 bosons. So, and d sigma by d omega, the differential cross section in the spin 0 state, or in the spin 0 combination, just looks like this, just like we had before. Okay, and this is just like for bosons. On the other hand, we could be in the total spin 1 state. And those are the only 2 possibilities. Now everything's opposite. The spin state is symmetric when you combine into a triplet spin 1 combination. Okay, and that means that the spatial wave function has to be antisymmetric. And so that means if I take my relative coordinate r and replace it by minus r, I should get a minus sign. So psi of r has to be equal to minus psi of minus r. In other words, it has odd parity. Okay, so now we can write down the consequences of that in the same way we did with bosons. We just have to know where to put the minus signs. So this time psi of r is going to be e to the I k r, k dot r. That's really e to the I k z in most cases. I'm allowing here for the possibility that my beams might not be in the z direction. But anyway, there has to be a relative minus sign between them. And the same thing for the scattering amplitude part. So there's an fk of theta minus an fk of pi minus theta instead of a plus sign. And then there's the radial part that stays the same. Okay, and now I know what to do. I just take those scattering amplitude part and square it to get the differential cross section. So d sigma by d omega, this is in the spin 1 combination, is fk of theta minus fk of pi minus theta. And when I square that out, the only difference is that the cross term is going to get a minus sign. So now it's minus 2 times the real part of fk star. And I've run out of room here, but fk pi minus theta. So notice this holds even if there's no, I'm talking about a potential that doesn't depend on spin, and yet I'm getting a different answer for the differential cross section just based on the fact that the electrons can't be in the same, have to be antisymmetric in total. So in particular, if you follow things through the way we did for bosons, this means at right angles, I expect a 0 differential cross section. So for theta equals pi over 2, d sigma by d omega in the spin 1 combination is 0. So one thing that means is if I look at right angles to the beam, any particles that I see out there from the scattering have to be in a spin 0 combination because the spin 1 combination vanishes. Another thing about this is that only odd angular momentum combinations can participate, just in general. So that's because the even ones in the Legendre polynomial expansion and the partial wave expansion vanish. So fk of theta minus fk of pi minus theta is 2 times the sum over only the odd combinations. So there's our 2L plus 1 times our Legendre polynomial, and then this really defines what the scattering amplitude coefficients have to be. Now, it's very common when you're doing an experiment like this that you don't actually have any knowledge or control of what the spins are. And so in that case, what you have to do is you have to average over the spins. So often, the spins are random and unmeasured. And in that case, the 4 spin states, notice it's 4 spin states, not 2, because the degeneracy of the s equals 0 combination is 1, and the degeneracy of the s equals 1 combination is 3. There are 3 of those. Okay, and so they're equally likely if everything's random. So the observed cross-section is the average. In fact, the observed differential cross-section is the average. And so then I can write differential cross-section. And we usually use the word unpolarized. Unpolarized is just a fancy way of saying we don't know what the spins are. Spin 1/2 fermions. If I were doing spin 3/2, it would be something else. Okay, this is 1/4 times the differential cross-section with spin 0 plus 3/4 times the differential cross-section with spin 1. And so if I just take those two results that I got and add them together, the things that weren't cross terms look exactly the same. And there's a partial destructive interference. So there's a minus sign, but no factor of 2 times what you would normally call the interference term. Okay, so the reason it's partial destructive interference is because the spin 0 part has constructive interference, just like for bosons. This has destructive interference, but there's more of them. And so you give it a minus sign, but no factor of 2. All right, there's one more thing I want to say about scattering of identical particles, and that's a famous tricky thing. And that is that there's an overcounting problem with identical particles. So for both identical bosons and fermions, let's say you've calculated the differential cross-section. So I'll say here there's an overcounting problem or a double counting problem. This does not arise if the particles are not identical. So if you've calculated the differential cross-section and you want the cross-section, the point is you should only integrate over half the angles. So it should only integrate 0 to theta to pi over 2, not pi, as you might, well, as you would normally do if you had non-identical particles. So why is that? Let's say you see a particle at the angle theta, and so you know that you're in a state where there's a particle at the angle theta. Okay, that's the same state as if there's a particle at pi minus theta, because if there's a particle at pi minus theta, there has to be one at theta also. So this is really the same state. And so that means you shouldn't count it twice when you're integrating over all possible final states. And so that's why you only integrate over half the angles, to avoid counting the same state twice. Okay, so need to avoid double counting. And so the way that comes in is when you define the total cross-section for identical particles, there's an extra, one way to do it is just put an extra factor of 1/2 times the integral over all angles times the differential cross-section. Okay, so the 1/2 is for identical particles and only identical particles. So if they're not identical, like you're doing neutron and proton, then if you see a neutron, if you see two particles with approximately equal masses, say, coming out at theta and pi minus theta, and then you look at the state where the other one's at theta and the other one's at pi minus theta, then it's not the same state and you should really count it separately. But for identical particles, you have to remember this factor of 2. And it comes in at the level of the total cross-section. You don't put a factor of 1/2 in the differential cross-section. That you just compute as normal, but you get this extra factor of 1/2. Okay, any questions on scattering of identical particles? All right, so the last thing I want to talk about today is going to be electron scattering from a nucleus. Okay, and so we have some heavy nucleus sitting here, and then an electron comes along and scatters and gets deflected by some angle theta. And if we put that beam so that it has a high probability of being very close to the nucleus, we can study the structure of the nucleus. So recall that we had the Rutherford scattering. So this is some z times E. Okay, and this is minus E on the electron coming along. And so recall the Rutherford formula for scattering from a Coulomb potential. And that looked something like this. D sigma by d omega is 4m squared z squared charge on the electron to the 4th power over h bar to the 4th q to the 4th. And in discussing this, I'm going to use this notation where q is the initial k minus the k prime. So this is k to start off with. This is k prime in the final state. And so we worked out before that this was 2k times sine of the scattering angle over 2. And it's just going to be nicer to write everything in terms of that q today. We just remember that it boils down to the angular dependence is built into the q. Okay, now when we got that Rutherford formula, we were not worried about the spin of the electron at all. And that's a good approximation if the electron isn't deflected very much. But more generally, you need to take the spin into account. And so when you do that, you need to include in the matrix element a factor that says if I measured the spin in the r hat direction of the scattered particle to be h bar over 2, that's got a non-unit overlap with the initial spin direction. And so if you work it out, there's an extra factor of that in the matrix element. And that factor turns out to be cosine squared theta over 2 in the matrix element. So when we originally did Rutherford scattering, we were pretending the electron had no spin. And I'm just telling you that this is what you get when you do it more carefully with the spin included. And so then you can write down the differential cross-section as this. So I'm going to translate my q to the 4th into energy just to make it look more like Rutherford scattering the way we originally wrote it. And the only difference is I've got this extra factor of cosine squared theta over 2. Okay, otherwise this is exactly what we wrote down for Rutherford scattering. And this is called the Mott formula or Mott scattering formula. Actually, it's kind of confusing because Mott has several scattering formulas named after him, but this is one of them. Okay, and so if you think about what this extra factor does, one thing it does is that if you scatter backwards, then theta is equal to pi, and theta over 2 is equal to pi over 2, and so the cosine of that is 0. So this extra factor is just telling you that if you send in an electron with spin along the beam direction, your probability to see it coming back at you goes to 0, because that would require flipping the spin. And there actually is a probability to flip the spin, but that's higher order in perturbation theory. We're actually working at first order in the Born approximation here. Okay, so, and all of this was also assuming that our nucleus was just a point, but at high Q, you can also probe the structure of the nucleus. And so I want to briefly say how that comes about. Okay, so here's a cartoon, a picture of the nucleus. It's just some ball of charge here, and it's got some radius. Okay, and inside it, it's got a distribution of density. And I'm going to call it the relative density is some function of position, and I'm going to put a prime on it. The prime is telling us that we're discussing the density as a function of position within the nucleus. Okay, so to probe this, you need Q to be bigger than about 1 over the size of the nucleus. Okay, and so that's a very small scale, but if we put in a large enough energy, then we can actually see what's going on inside the nucleus. So this relative density, what do I mean by that? What I really mean is that if I integrate over all possible positions within the nucleus of this density function, okay, that's going to be equal to 1. In other words, it's saying, really, this is the probability to find the charge of the nucleus within some little volume. If I integrate that over the whole volume, I should get 1 by normalization. Okay, and so what does that mean? It means that if before I was writing down a potential, I guess I'm going to make this spherically symmetric, even though it's not exactly spherically symmetric. Before I would have written down this, minus z e squared over r. Okay, but now the effect of this change is that I'm going to write down minus z e squared. We go back to what we learned in electrostatics, that the potential is this density function divided by 1 over r minus r prime. Okay, so this is just from electrostatics. Okay, and then if I put back that my n was a delta function, that would bring back this. This is the point-like approximation, point-like nucleus. And so to get back, what I would do is I would say, let my relative density function be a 3-dimensional delta function. That's just saying all the charge in my nucleus is concentrated at the single point r prime equals 0. Then I get back the formula that we originally derived the Born approximation for Rutherford scattering. Okay, so now let's just see what that will change when we do the Born approximation again. So in the Born approximation, we're going to take, so in the Born approximation, we had this formula. There was an integral over all positions, ze squared e to the I q dot r divided by r. And now we're going to put in our new potential instead and see how things change. So now our new potential is an integral over r prime, e to the I q dot r. But now there's an n of, let me rewrite this, e to the I q dot r, but now there's an n of r prime divided by this r minus r prime factor. Okay, and so that's really the only change within the Born approximation. Of course, the Born approximation isn't perfect, but so that's what we get. And now we're going to do a trick. First of all, I can pull out the constant, ze squared. And then I've got my two integrals to do. Let me write down the answer and then I'll explain what the trick was. So I'm going to write e to the I q not dot r, but into r plus r prime. Okay, and then I still have my factor of n of r prime, but now I'm going to divide by the magnitude of r instead of the magnitude of r minus r prime. So what did I do there? All I did is I shifted my integration variable. So I shifted from r to r plus r prime, right? So the reason for doing that is now the denominator just gets turned into 1 over r, which, by the way, now I see that I can, in fact, pull that out of this integral because it doesn't depend on r prime anymore. I'm not shifting r prime, so this didn't change. And then the exponent changed according to this shift. Okay, so that's just a neat little trick. And now we can rewrite things like this. I'm going to pull everything that I can out of the r prime integral. And everything that I can means e to the I q dot r divided by r. And now let's write behind, what's next is everything that's left behind, which is e to the I q dot r prime, n of r prime. So the whole strategy here is based on separating things into an integral over the nucleus that doesn't involve the integral over r. Okay, and so if I look at this part, that part is exactly what it was before in the Born approximation for a point-like nucleus. And so we know that that's 4 pi over q squared. And this other part is just some function of q, because I'm integrating over r prime. It also depends on the structure of the nucleus. So we're going to define this to be a function that depends on the nucleus, and it depends on q. It doesn't depend on r prime because we're integrating over r prime. So that's some function that if we could measure it, we would learn something about the structure of the nucleus. And this is called the form factor. Okay, and if the nucleus were point-like, it would just be 1. So the deviation of this form factor from 1 is telling you about the structure. Okay, and the reason it would be 1 if the nucleus were point-like is then I would be plugging in a delta function here. The delta function would have its argument vanish at r prime equals 0, which would make this 1. And so that's why the whole thing would just be 1. Okay, so what we've done here is we've calculated the change in the Born approximation due to having a nucleus that's not exactly point-like. And so we can summarize this, that this is for the scattering amplitude. And so for the differential cross-section, what we've learned is we can separate it into two parts. There's the part that there would be if the nucleus were point-like. And then there's the extra factor, which is the form factor of the nucleus as a function of Q squared, because I square the scattering cross-section to get, I square the scattering amplitude from the Born approximation to get the differential cross-section. Okay, so just to see how this goes, we can do an approximation where we expand in Q times the size of the nucleus. And we're going to assume, even though it's not quite true, that the relative density is a function of radius. The reason it's not exactly true is because the proton has spin, and so the density will change depending on the relative orientation between the vector r and the spin direction. So we're assuming here spherical symmetry. But if you're not in a spin eigenstate, if you're averaging over the spins of the nucleus, then this is actually an okay approximation. But now we can just work out what this form factor is going to be with those assumptions. F of the nucleus as a function of Q is supposed to be this. Integral over all r, e to the I q dot r times n of r. Okay, and our strategy is just to expand that exponential. So here I'm going to write my n of r, and then I'm going to write 1 plus I q dot r plus I q dot r squared, which I'm going to write like this, I squared, q squared, r squared. And then because it's a dot product, I take the dot product of the two directions. Okay, and that's equal to the cosine of the angle between those two vectors. Okay, and then this continues on, but I'm neglecting all those higher order terms. And so now I should say cosine squared theta because I squared it there. And so now if I do this integral, this thing has to vanish because for every contribution with one value of r, there's a contribution of r the vector, there's a contribution from the opposite direction. And because we're taking q dotted into it, q is a constant vector from the point of view of the integral, this thing has to vanish. Another way of saying it is that because it's spherically symmetric, if this thing didn't vanish, if I just look at this integral here times that, there's no special direction for that thing to point, so it has to vanish. Okay, so that part's 0. And then this part, if I do the integral of n of r, we defined that to be 1. And so this whole thing is 1 minus, from squaring the I squared, q squared. And then I still have an integral to do. So there's an r squared from the d3r. There's an r squared from here. I'm going to write that as another r squared. There's my n of r factor. And then I've got the angular integrals to do. And I see that what's going on here is I've got an integral cosine squared theta. Okay, and oh, I forgot one thing, which was when I expanded out the e to the I q dot r, there should have been a 2 factorial. So there should have been a 2 1/2 here. So I'll include that. Okay, I think I've got everything straight here. So this factor is 2 pi. This factor is 4/3. No, sorry, 2/3. Okay, and so if I put everything together, this is 1 minus q squared divided by 6 times an integral 0 to infinity dr 4 pi r squared times my relative density function. Okay, and then I should admit that I've made an approximation here. There are higher order terms. Okay, so if I think about it, what is this? This is really the average radius. It's like an expectation value of the radius of the nucleus. So I can call this R nucleus bar squared. And so all that we've learned here is that the form factor for a nucleus to first approximation is 1, which it would be if it were point-like, minus q squared over 6, that depends on the scattering energy and the scattering angle, times the radius of the nucleus squared. And so if I can measure the form factor by measuring the differential cross-section, I can check out that it hopefully matches to this form. And if it does match to that form, then I've learned something about the radius of the nucleus squared. Okay, so this is a sort of baby version where I've left out a few of the higher order details, like relativistic effects turn out to come into play, and other effects involving the spin. But a more sophisticated version of this has indeed been used to probe the structure of the nucleus. So a more sophisticated version. So among the things you have to include are nuclear recoil. The nucleus isn't completely immobile. It has a large mass, but it recoils a little bit. Relativistic effects. I'll just leave it at that. Has been used to measure the non-zero nuclear structure or size of the nucleus. So in fact, this is in current events, this is sometimes called the proton radius puzzle, because different ways of measuring the radius of the proton give slightly different answers. Okay, so if you do the scattering method that we've been talking about to get the form factor and then interpret the form factor in terms of a radius, you get the radius of a proton to be something like 0.875 times 10 to the minus 13 centimeters. And if you do hydrogen atom spectroscopy, you get something similar. But if you do muons with protons and you look for resonances, which should in principle give you the same thing, and there's a lot of details here that require some care, but you get a slightly smaller number. So they've been quite going back and forth on this. The latest I heard is maybe things aren't a problem after all, which is my guess what the final outcome will be, but it's still not completely settled. Okay, so this is actually something useful. All right, so we're out of time. Thank you all for sticking with the course through to the end. And Friday, of course, is a reading day, which is why we're not having class. And I am just about, in fact, I will do it right now. I have just sent you all the final exam, which has the rules on it for what you're allowed to consult and not allowed to consult and all that stuff. So good luck on that. And I will also be sending you the homework 10 solutions and the graded versions of that. All right, so again, thank you very much for sticking through. And if there are any questions on today's lecture, I'll be happy to answer them.
Thank you.
Thank you so much.
And if not, I will hopefully see you around under better circumstances.